One of the most all-pervasive and ubiquitous features of our experience of the physical world, so common a part of our everyday experience that we rarely bother to think about it, is the fact that we seem to be able to remember the past and affect the future, and not vice versa. How nice it would be if I could go back in time to that party the other night and correct that awful social gaffe that I made. But I know I can't. How nice it would be if I could go forward in time and know the result of tomorrow's horse race and place my bet accordingly. Alas, I know I cannot do that either. So this fact about the world, that we can remember the past and affect the future, not vice versa, seems to be the most basic part of our experience. Connected with this, though it's not quite the same thing, is the fact that we seem to be able to tell, generally speaking, when a movie of some everyday event is being shown properly, or when the movie is running backwards. So let me just give you a couple of examples of that. Okay, so here we go. Now, our two young lab assistants are indeed energetic, but they are not quite that energetic. So let's show this way. And now you see, you can tell when the movie is being shown properly and when it's being shown backwards. One more example. Looks fine, right? Again, you can tell. Right? Now, why is this a problem? Well, it turns out that with one very small and probably unimportant, although one cannot be quite sure, one unimportant exception, the basic laws of physics do not appear to care whether time is run forward or backward. Let's start with probably the best known law of basic physics, namely Newton's laws. So remember, Newton's first law says that every body remains in a state of uniform motion or rest unless it is acted on by some external force. Now, there's no mention in that law about the direction of time. Newton's third law says that every action has an equal and opposite reaction. Again, no mention of the direction of time. So if there is any reference to the direction of time in Newton's laws, it must come in the second law. Well, Newton's second law tells us that force is equal to mass times acceleration. Now, the force, it might be due to gravity, say, so again, no reference to time there. What about acceleration? Well, acceleration is the rate of change of velocity. If you imagine that you are sitting on a merry-go-round, say, and the merry-go-round is rotating like this, then you will feel a force on your back because you are accelerating towards the center of the merry-go-round. If the time is reversed so that the merry-go-round runs backwards, you see the velocity is reversed, but you still feel the same acceleration towards the center here. So when time is reversed, acceleration is unchanged. In other words, Newton's three laws work just as well backwards as forwards. Well, you say, well, but that's okay, but what about electromagnetism? Doesn't electromagnetism tell us the difference between backward and forward direction in time? For example, suppose I have a magnetic field, and so it's up, and I have an electron which is moving in that magnetic field. And so, I don't know if I've got this right or not, but let's say it'll go anti-clockwise, like so. Now, if the movie is run backwards, then the electron will appear to go like this. So at first sight, this says that tells you about the direction of time. But there's a catch, unfortunately. How did you produce the magnetic field? You produced it by currents in some kind of coil. If you change the direction of time, then the currents run backwards and the magnetic field is now down. So the electron indeed now goes around this way, so you can't tell again. What about quantum mechanics? Well, at first sight, if you read a standard textbook of quantum mechanics, it does seem to rely on a particular direction of time, because typically in a textbook problem, you start with an initial state to which you assign a wave function, and then you perform operations with Schrödinger's equation, and eventually at the end you maybe make a measurement. So at first sight, that appears to be asymmetric in time. That's actually deceptive. And there was a very famous paper by Aharonov, Bergman, and Lebovitz way back in 1964, which argued, I think very convincingly, that you could start with a completely symmetric, time-symmetric version of quantum mechanics, and then by imposing certain kinds of condition, you could either get our standard textbook quantum mechanics, in which time appears to run forward, or a time-reversed version, in which it appears to run backwards. So again, there's really no preference there. It's a matter of choice that you interpret it in this particular way. Associated with that, there's another interesting... oh, yeah, okay, sorry. So this is just an illustration. Now, this is a case, I think... let's see if I can get just one. Let's go back a moment. Yeah. Yeah. Now, in this case, there's one movie, and now I'm going to show the next one. Now, there you could not tell, I think, could you, which one is being shown forward and which backwards. So that illustrates that when you're just dealing with good old Newton's laws in a rather simple situation, you really can't tell. Now, associated with this is another question. Is it correct in terms of basic physics to say that the past causes the future? At first sight, well, yes. Here's a standard textbook problem in elementary mechanics. You have a cannon here, which is going to fire a cannonball. And what the textbook will tell you, possibly, is the initial position and velocity of the cannonball. And then it will ask you to calculate the trajectory, motion of the cannonball, and perhaps to decide where it comes out, where it lands here. And so, if we know the initial position and velocity, we can determine the exact trajectory. And you can actually make a much more general statement, which involves many different particles and so forth. And there was a very famous thought experiment due to Pierre-Simon Laplace, famous 19th century mathematician and physicist. Laplace said to himself, suppose that we imagine a demon whose faculties are so acute that he knows the position and velocity of every particle in the universe, and also knows all the forces acting on those particles. Then the demon would be able to predict the whole future of the universe. Nothing for him would be uncertain. This is the famous paradox, if you want to call it that, of Laplace's demon. And many people have understood that argument to be an argument against the existence of free will. But there's a snag in this argument. As we saw, Newton's laws are time symmetric. So you can also infer the complete trajectory from the final position and velocity, or from some intermediate position and velocity, or even from initial and final positions. For those of you who are physicists, technically the argument is that Newton's second law is second order in time, so any two pieces of information are sufficient to determine the whole trajectory. So that says we might just as well say that it is the final position and velocity which caused the initial one, not vice versa. So in the early 19th century, people started to worry rather seriously about this problem. And a very famous, a very distinguished group, mostly of French physicists, came up with a quite different kind of argument about the direction of time. And it's really based on the behavior, not just of a single particle, but of very large collections of particles. Imagine, say, we have a gas which is confined to a small volume, which is part of a larger one. And imagine that you can pull away at some time the partition. Once you've pulled the partition away, the same gas will expand and fill the whole volume. And we all know that however long you wait, this gas is not going to spontaneously reassemble itself into this state. So at least at first sight, this gives us some way of defining the direction of time. And let's make that just a little more technical. And now I'm going to give you an example which I can always use when I give this lecture in the United States, because everyone has the relevant experience. I'm not sure if you will have it in Japan, but I suspect that you anyway know what I'm talking about. It has to do with parking a car. Suppose that you are taking a driving lesson. Then your instructor will take you to the driving school car, which is parked along the curb here. And he will ask you to drive the car out into the road. And generally speaking, you don't have too much difficulty doing that. On the other hand, when at the end of the lesson, he will ask you to back into this parking space here. And you all know, well, at least those of you who have taken driving lessons all know, that this is much more difficult than this. Why is that? Well, crudely speaking, because in this case, you had a large final space to go into. You could arrange to end up in many places in the road. Whereas here, you've only got a small final space to get into. So these French physicists came up, French and German physicists came up with the idea you can define a concept of disorder which has to do with the available space or with the number of available states. Now, it actually, for technical reasons, it turns out you don't want to define the disorder as simply proportional to this. It's more convenient to define it as proportional to the logarithm of the disorder. And then you define a quantity, the so-called entropy, S, which is a measure of disorder. In fact, there's an equation which is often associated with Ludwig Boltzmann, famous German, or rather Austrian physicist, the 19th century. It says that the entropy is a constant times the logarithm of the number of available states. And that's how you come to the idea of the second law of thermodynamics, which, crudely speaking, says that entropy always increases with time. And at first sight, that looks very natural, because, after all, it is much easier to go from here to here than it is from here to here. And so it seems very natural, in fact, that disorder and therefore entropy should increase with time, and therefore you ought to be able to define the future as the direction of increasing entropy. And at first sight, that's the origin of time asymmetry. And many of the not-so-careful textbooks will simply leave it at that. But there's a problem. In this argument, you're always assuming that it's the initial states and not the final states which have low disorder. So let's just say a little about that question. Let's imagine a thought experiment which involves the shuffling of a deck of cards. So I'm going to imagine that we have a closed room with a lock on the door here, and inside we have a mechanical shuffler. It's a machine which will shuffle the cards. And we have a camera which will, first of all, make sure that no one breaks into the room, and secondly, it will take a picture of the cards at any particular point in the shuffling process. Now, imagine that we come back from lunch, let's say, and we inspect what the camera is showing, and we see that we have got this ordering here, which, as most of you will know, is a very special kind of ordering, not the kind of thing we would normally expect to occur by accident. But, well, what is our thought? Well, our first thought is that maybe some kind of super Houdini had somehow managed to get into the room and prepare the cards like that. But the camera doesn't show anything like that, so we know that hasn't happened. So what do we expect? Well, we expect that if we go, if we now let the machine go on shuffling, then gradually this deck will become less ordered. Okay, so indeed, disorder will increase with time. But there's a snag here. The inverse of a shuffling process is itself a shuffling process. So what if we go backwards in time? We would then expect to see the disorder increasing in this direction rather than this one. So it does not seem at first sight as if the idea that the initial states are always perfectly ordered will help us. So at first sight, it's very tempting to think that the direction of time has something to do with the fact that we human beings can prepare a deck like this, but we cannot, as it were, retropair it. In other words, we cannot, in fact, arrange things so that after a certain time, we will automatically get this perfectly ordered situation. That's sometimes called retropairing, and this is something we know we cannot do. But then it doesn't really seem that plausible to associate the direction of time with what we humans can and cannot do. To illustrate that, let's consider a purely natural process in which there are no human beings involved. So imagine we have a rock which is perched unstably at the top of a cliff. And eventually, because of natural erosion, it becomes detached, it falls down the cliff, it falls into the lake, it'll cause waves which radiate outwards, and eventually it will come to rest on the bottom of the pool. Now we know that if we were to show the movie of this process backwards, we find that the rock lifts itself up from the bottom of the pool, the waves come inwards from infinity, the rock spontaneously moves up the cliff and reattaches itself at the top. And we know that doesn't happen in nature. So the direction of time doesn't really seem to have much to do with what we human beings can or can't do. There are no human beings involved here at all. Well, as I say, this really caused people in the early 19th century a lot of headaches. And eventually a rather brilliant solution was found, or was proposed, by Ludwig Boltzmann. This is the tombstone of Boltzmann in the Zentralfriedhof, the central cemetery in Vienna. And you see above his bust, there is inscribed this famous equation, S equals K log W, which is a little ironic, since as far as anyone knows, Boltzmann himself actually never wrote down that equation. So it is strongly associated with his name. Anyway, here is Boltzmann's solution. He said to himself, well, the general principle of thermodynamics indeed says that left to themselves, things tend to a state of maximum disorder. Any of you who happen to have small children and have left them alone in a room with, say, a few balls of wool or something like that, will know that's certainly a general principle. So on average, Boltzmann said, the universe is in a state of maximum disorder. But occasionally, there will be fluctuations away from that state of maximum disorder to a lower disorder state. And that will be rather local and only last for a limited time. So suppose indeed that the fluctuations have gone something like that, or are going something like that. And supposing that we live at this point here, then we would see the disorder as increasing in time in this direction. And that would be the direction of the future as perceived by us. If, on the other hand, we were sitting at this point here, then we would see the future, see disorder increasing in this direction, and that would be the direction of the future as perceived by us. But, of course, that raises the question, well, isn't it very improbable that we would be sitting in one of these fluctuations rather than out here? And then Boltzmann actually gave an answer which anticipated some modern ideas by 150 years. He said, well, the answer to that is that if we were indeed sitting in either of these regions here, the conditions would just not be suitable for human life to exist. So we would not be here to ask the question. And that is an anticipation of the so-called Anthropic Principle, which is nowadays much discussed in cosmology. Let me just say a brief word about that. In the current theory of elementary particles, there are all sorts of numbers which you just have to accept, for which there appears to be no particular explanation. For example, the mass of the electron is about 1 over 1800 times the mass of the proton. The charge of the electron in a particular series of units is about 1 over 137, and so on and so on. There are about 20 different numbers of this type, and the present theory, which we have of elementary particles, the so-called standard model, does not explain these. And so one possible answer is that the reason why these numbers have the values they do is simply that if they did not have these values, human life would not exist, and we would not be here to ask the question. That's the so-called Anthropic Principle. It's very controversial whether this is a real explanation or not, but it is much discussed. In any case, going back to Boltzmann's idea, unfortunately it turns out that we actually do not appear to be living in any special place in the universe. As far as we can see, and now we can see for many billions of light years out into the universe around us, it looks as if the rest of the universe is pretty much like our immediate neighborhood. So the idea that we're in some special place does not seem really to work. Well, at this point, let me just go on and just talk, take a slightly different direction and talk about the different arrows of time. First of all, we have the psychological arrow, that we can remember the past and affect the future, but not vice versa, as we said at the beginning. The biological arrow, plants, generally speaking, plants and animals seem to start small, grow bigger, and eventually die. There's the electromagnetic arrow of time. Apparently, both light bulbs and stars emit radiation and don't absorb it, even though the basic laws of electromagnetism are consistent with them doing both. So let me just, yes. So this is the movie. This is some source emitting radiation. And now if we go on, now you see that solution is also consistent with the laws of electromagnetism. So why doesn't it occur? Well, let's just go back a moment to see if I can do this. There's the thermodynamic arrow of time, which we've already noticed, that disorder or entropy increases. And finally, there's the so-called cosmological arrow of time. As far as we know, the universe right now is expanding and not contracting. So it's interesting to ask, is there any obvious relationship between these different arrows of time? Well, I think the relationship between these two, I think, is I think fairly plausible, at least. There is no logical contradiction in the idea that I should be able to remember the time when my hair is even whiter than it is today, and I'm even more feeble and close to death. And I should be able to affect the time when I was a small child in my mother's arms. I say there's no logical contradiction about that, but I think most of us would feel with rather plausibly that there have to be good biochemical reasons, say, why that's not possible. So I think the relationship between these two is not so mysterious. Again, there's a rather simple relation between the biological and electromagnetic arrow. After all, how do plants grow? They grow by receiving radiation from the sun and turning it into energy. If the sun were to be sucking in radiation rather than sending it out, then that would not work. So again, I think this is rather plausible. Again, I think it's fairly plausible to imagine that the electromagnetic arrow is a rather special case of the thermodynamic one, because after all, the state in which a star has radiated a lot of its energy turns out to have much more disorder, much more entropy, than the state in which all the radiation is contained in the star. Again, not so mysterious. The final one, however, is a little more problematic. can we relate the thermodynamic arrow to the cosmological one? And there we actually run into a difficulty. Yeah. So this raises the important question whether cosmology can explain thermodynamics. In the standard so-called Friedman-Robertson-Walker model of the universe, all scenarios, and are independently variable, I'll explain that in a moment, they all agree about the past. So they all agree that if we're here and we go back in time, then eventually we get back to a point at which the universe was infinitely dense and infinitely hot. That's the so-called hot Big Bang. So that raises the question, why is the disorder apparently low at the small end, at the hot Big Bang? You might, incidentally, you might think that it's rather peculiar that since the universe was very hot, it would have very low disorder. But that turns out to be the case. It's a rather odd situation. So that raises the important question, why is disorder low at the small end, at the hot Big Bang? And I have to say, I don't know the answer. And I'm not embarrassed about this, because even the real heavyweights in this field, the people whose names you've all heard, they don't know the answer either. They argue furiously about this question. But let's just go on for a moment and just think about possible futures of the universe. Now here, it turns out that there is a particular quantity, the so-called mass density of the universe in appropriate units, which is very important for this question. If this parameter, capital omega, is less than 1, then we have a so-called open universe, and it will go on expanding forever. If omega happens to be exactly 1, you might think that was very improbable, but there are plenty of theories in which that is true. If that's the case, then the universe will eventually flatten off and expand slower and slower, and eventually not at all. Finally, in some sense, this is the most interesting case in this context. If we have omega greater than 1, we have a so-called closed universe, and the universe is going to expand to a maximum size and then contract again to a state where, again, it's infinitely dense and infinitely hot. That's the so-called hot big crunch. So that raises the question, what if the universe is indeed closed? That seems to be not very probable, but it's not absurd to imagine that. Suppose that indeed this happens. Then when we pass here, going down here, is the disorder increasing or decreasing? And which way would any humans who happen to be living in this period, if they could, which way would they see the future? This way or this way? Again, this is a question on which the real big names in the field even disagree. So as I say, I'm not too embarrassed not to give you a definite answer on that. Well, let's just put that aside for a moment. Let's just assume, for the sake of argument, that somehow we can explain the second law of thermodynamics in terms of cosmology. That's on the average. But suppose that nevertheless there are small fluctuations in which the direction of time appears to be reversed. Now that at first sight seems a very odd idea, but it has an analogy. For example, when you think about the behavior of a magnetic system like, say, iron. Now you know that in iron, if it's below the so-called Curie temperature, on average, the spins tend to point in the same direction. at least in a single domain. Nevertheless, there is a non-zero probability that if I just take a small region for a limited period of time, the spins may reverse themselves in that. This will just be a standard so-called thermodynamic fluctuation. Now, we could suppose that possibly this happens with the direction of time, that on average it looks as if the second law of thermodynamics works. But nevertheless, there might be these small regions of space and time in which it's somehow reversed. That seems a very weird idea indeed. Why would anyone even think of such a crazy idea? Well, there is a reason actually why we might take it seriously. It goes something like this. There is a series of very famous experiments. For those of you who are physicists, you may know these as the so-called Einstein-Podolsky-Rosen-Bell experiments. It goes something like this. You have an atomic source which emits pairs of photons, quanta of light, back to back. And we arrange to switch each of these photons into one of two possible measuring instruments. And we do the same at the other end here. And then the raw data which we measure in this experiment are the correlations between the answer to the question which this device asks and the one which this device asks. And it turns out to be an experimental fact that the correlations which we observe, well, first of all, it turns out they're consistent with the predictions of quantum mechanics. But that's not what we're really interested in here. What's more interesting is that these correlations are inconsistent with any theory which embodies three principles. The first is objectivity, which we can take as the idea that single photons carry individual properties in their own right. I could talk about that at much greater length, but that'll do for now. The second postulate is locality, that is that no causal influences can be transmitted faster than the speed of light. And the third is, well, induction is not a good word, but it's the standard arrow of time, the idea that the past causes the future and not vice versa. Well, there are all sorts of reasons why we might not want to throw away objectivity or locality. So how about contemplating the idea that sometimes, for example, in this kind of situation, induction fails? In other words, there might be a causal influence coming from the future back to the source in this experiment. Well, this turns out to be formally okay, but then you get a very nasty question about whether it can be reconciled with the macroscopic second law, the increase of entropy. Incidentally, this whole question of the arrow of time and whether it can reverse itself in limited circumstances is, I think, rather important for the question of free will. I think that I just raised my arm voluntarily. But Laplace and his followers will say that's not right. Basically, the fact that you raised your arm is a consequence of the fact that 5 minutes ago, all the atoms of the universe were in a particular state. And that is what, in some sense, determines the fact that I'm going to raise my arm. I say, no, that's not true. Rather, it is the fact that I raised my arm that determined the state of the universe 5 minutes ago. Can I get away with that? That raises some very, very subtle questions, I think. Again, I don't really claim to know the answer, but I think it's an idea well worth exploring. So finally, and I'm going to conclude, if you look back at the history of physics over the last 500 years, you see that every really major revolution in physics has involved the overthrow of something which until that time was thought of as the most obvious common sense. It's obviously common sense that the sun goes around the Earth, until Copernicus told us otherwise. It's obviously common sense that objects which are not observed behave in the same way as when they are observed, until Heisenberg told us otherwise. It's obviously common sense that the universe is unchanging in time, until Hubble told us otherwise. There's one major feature of our more common sense principle about our experience of the physical world that has not been challenged in any of those revolutions, and that is the idea that the past causes the present and the present causes the future, and not vice versa. I'm personally convinced that if at some time in the next 10, 100, 500 years there comes about one more major revolution in physics, it will involve a challenge to this idea in some form or other. Now, at this point, of course, you're going to ask me, what is this new theory going to be like? And to that question, I can only give you the answer which the famous jazz musician Louis Armstrong is said to have given when someone asked him where jazz was going. And his reply was quite simply, "Man, if I knew where jazz was going, I would be there already." And so that has to be my answer. Thank you.